and I've got the great pleasure in inviting Professor Martin Rees to tell us everything he knows about cosmology.
Well, I've got to fill up the hour. Yes. Well, this is a lecture in honour of Gerald Whitrow, a member of the Society who some will remember. He was interested in the history of our subjects, and also he was a speculative thinker. And so in homage to him, I'm going to give you some bits of history and some speculations too. Let's have some historical thoughts. That was Professor Whitrow, and this is a picture of Einstein and Eddington in the 1930s, probably talking about whether the universe was expanding or not. And here's Fred Hoyle and Lemaitre in the late 50s, probably talking about whether there was a Big Bang or not. And indeed, until about 1960, cosmology was a subject with almost zero empirical content. Astronomers couldn't probe deep enough into space, far enough back into time, to detect cosmic evolution, even if it occurred. And also, incidentally, there was little evidence then that the universe had the large-scale uniformity and the isotropy, which was a feature of the theoretical models that were discussed at that time. But the subject was transformed, of course, in the 1960s through a number of innovations. It was Martin Rees in Cambridge who studied radio sources and inferred that there were more far away in the past than now. This was the first evidence against the steady-state theory. And then in 1963, Martin Schmidt led the discovery of quasars, which opened up the possibility of large redshifts. I'll come back to that a bit later. There was also a renaissance in theory at this time, I'd like to mention the great leaders of the theoretical innovation. There was John Wheeler, who led the American group based at Princeton. There was Eldovich, who led an equally strong group based in Moscow. And in the UK, there was perhaps the strongest group of all, which was pioneered by new ideas and relativity by Roger Penrose and fostered by Dennis Sharma, who was a mentor to a whole generation of students who followed up on many of these ideas. And today, 50 years after all these discoveries, astronomy and cosmology is still on a roll. We can with confidence trace cosmic history now back 13.8 billion years to a moment only a billionth of a second after the Big Bang. Our universe's expansion rate, the mean density of its main constituents, and other key numbers are pinned down to a precision of a few percent, and we can detect redshifts as large as 10. We're learning what galaxies are made of and how cosmic structures, galaxies and clusters, emerge and evolve from amorphous dense beginnings. Computer simulations and data have corroborated a scenario for cosmic evolution known as lambda CDM. And when the history of recent decades gets written, I'm sure this amazing progress will be acclaimed as one of science's greatest triumphs. I think it deserves to be up there with the genome and plate tectonics, for instance. Well, all advances open up new questions that couldn't have been posed before then. And the subject has changed in its character. In fact, Werner Israel divided cosmology into two types: the chess players and the mud wrestlers. The chess players are those who are tackling fundamental questions, such as why does the universe expand the way it does? Why does it contain the mixture of entities that are in it? But for the mud wrestlers, cosmology is the grandest environmental science. They're trying to explore the complex and messy physics, whereby galaxies, clusters, and their constituent stars and gas emerged and evolved during cosmic history. The game changer which introduced modern cosmology was, of course, the discovery by Penzias Wilson 54 years ago that intergalactic space isn't completely cold. It's warmed to 3 degrees above absolute zero by weak microwaves, which were quickly discovered to have an almost exact black body spectrum. This is a so-called afterglow of creation, the adiabatically cooled and diluted relic of an era when everything was squeezed, hot, and dense. And it's one of several lines of evidence, probably the most important of all, which have allowed us to firm up the hot Big Bang model. And even by 1970, we had a time chart like this. The background radiation is a direct messenger of the era about 300,000 years after the Big Bang, when the material recombined about 3,000 degrees. And calculations were done by then of nuclear reaction in the first 3 minutes, showing that the helium-deuterium abundances were determined back then and were in accord with observations. That was the second key pillar of the Big Bang. But before going further, let's address an issue that might seem puzzling to people. Our present complex cosmos manifests a huge range of temperatures and density, from blazingly hot stars to the dark night sky. And people sometimes worry about how this intricate complexity emerged from an alleged amorphous fireball. It might seem to violate the second law of thermodynamics, which describes the inexorable tendency for patterns and structures to decay or disperse. But the answer to this seemingly paradoxical situation lies in the force of gravity. Gravity enhances density contrasts rather than wiping them out. A slightly overdense region expands slower and its density contrast is enhanced. And it eventually stops expanding and separates out. And this movie shows a simulation of part of a virtual universe. The expansion scaled out, so the picture stays the same size, but you can clearly see the incipient structure unfolding and evolving. The blue is the dark matter, 5 times more than ordinary atoms, and the red is the atoms themselves, the gas, which can radiate, dissipate, and form stars. Movies of this kind portray how galaxies emerged. And in galaxy-scale clumps, gravity enhances the contrast still further, gas is pulled in and compressed into stars. Each galaxy is an arena within which stars, planets, and perhaps life can emerge. And there's one very important point. The initial fluctuations fed into that computer simulation weren't arbitrary. They're derived from actually observed fluctuations in the temperature of the microwave background, which have been beautifully delineated over the whole sky by ESA's Planck spacecraft. This map is a projection of the whole sky, where some patches are hotter than average, overdense regions, and some are slightly cooler than average, the underdense regions. The amplitude of the fluctuations is only 1 part in 100,000. I'll come back to this later. But the important point is that if you take those fluctuations and compute them forward, you end up with structures, galaxies and clusters, which accord with what we observe. And that's indicated rather schematically in this diagram due to Max Tegmark, where the solid curve indicates the RMS density fluctuations on different scales and various types of data, clusters, galaxies, intergalactic clouds, etc., are plotted, and there's a pretty good fit. And there's more data which corroborates this. And incidentally, I've oversimplified what I said about the Planck data, because actually the fluctuations which you saw, if you analyze their spectrum, the amplitude as a function of wavelength, they have a rather complicated structure imprinted on them before recombination. And that's illustrated here. What this shows is different angular scales, the small ones on the right, large scales on the left, there's high harmonics on the right, and you get a fit if you pick the right density for matter, both dark matter and baryons, to this very complicated curve. And it's a huge achievement that we are able to understand the reason why we get this particular spectrum of fluctuations. I would say this diagram is one of the most amazing achievements, where the theory predicted that there would be these wiggles due to the sound waves and their amplitude before recombination, and we actually observe something like that. And I'll come back to the importance of the big peak in a few moments. So this is measuring the microwave background, 3 degrees, to a precision of 1 part in a million, and analyzing its spectrum and getting an amazing fit to pre-existing theory. Well, we know that the universe was very different in the past. I mentioned Martin Rees and Schmidt, and we've had a rise in the density in the distance that we can probe. This just shows the highest redshifts as a function of time. By 1970, we had redshifts of more than 3 for the quasars, and it's gone up. We have quasars more than 7, and the galaxies have actually overtaken them. We have galaxies and gamma-ray bursts out to a redshift of 10. And we've also had a succession of surveys of galaxies. That's Martin Schmidt, and this is the gamma-ray bursts, which are observed out to redshift of 10. So we can really probe back to when the universe was about 4% of its present age. And we also have maps of the sky. We have surveys. This is one showing the galaxies within 600 million light years. Here's the 2-degree field survey. And we're going to hear more about distant galaxies in the talk from Rebecca, which comes just after my talk, so I won't say much about it. But this is a picture of a patch of sky, and the smudges here are in many cases very distant galaxies being seen when they've only recently formed. And we've had, as I say, a succession of surveys of this kind. All these smudges are galaxies so far away their light set out more than 10 billion years ago. We're looking back to a very early stage, the first nonlinearities in the universe. But how much can we actually understand about the morphology of galaxies? Some which are disk-like, like the Milky Way and Andromeda, and some which are ellipticals, and what goes on inside them. Here again, large bodies of data and simulations have helped. And the huge amount of data from Gaia, of course, has been crucial for our galaxy. And the other thing we've learned is that galaxies aren't just assemblages of stars and gas and dark matter, but they have at their center black holes. And it's these black holes which, when fueled with gas and magnetic fields, can power galaxies and can also inflate the giant radio-emitting lobes that surround some galaxies and were detected by Martin Rees even before one could detect optical objects at that same distance. Well, physicists who study particles can probe them, crash them together in accelerators at CERN and see what happens. Astronomers can't, of course, do experiments. They certainly can't crash real galaxies together, and galaxies change so slowly that in a human lifetime you only get a snapshot of each one. But of course, astronomers can do experiments in a speeded up virtual universe. And here is a rather nice picture showing 2 galaxies colliding, a real train wreck. Here the gravity of the stars and gas is calculated, and eventually it will settle down as an amorphous galaxy. And this will happen, by the way, to our galaxy when it's hit by Andromeda in about 4 billion years. It won't affect the solar system very much, because even after this, the stars are only about twice as close packed at most as they are today, so the nearest star will still be a long way away. Well, having done calculations like this, one then looks up at the sky, and you see systems like this. And this is 2 galaxies, which if you came back in another 50 million years, you'd probably find had merged, as in that movie. And we suspect, indeed, that galaxies have, in many cases, grown by mergers. Our own galaxy may merge with Andromeda, and it's merged with smaller ones. I guess when you merge with a small galaxy, you call it acquisition, not a merger. So our galaxies had lots of acquisitions, if not any major mergers. Well, importantly, As I say, we find by doing these simulations that you get the best fit if you put in about 5 times as much dark matter as there in ordinary atoms. And this was gradually realized during the 1970s as being an important constituent of galaxies. Well, here's the time chart again. And as I said, we can trace cosmic history back to 1 second, when the temperature is about an MeV, and that's when helium and deuterium formed. And we can probably be confident back to about a nanosecond. That's when each particle had about 50 GeV of energy, as much as can be achieved in the LHC accelerator in Geneva. And at that time, the entire visible universe was squeezed to the size of our solar system. But questions like, what caused the fluctuations? Why does the universe expand the way it does? Why does it contain the observed mix of atoms, radiation, and dark matter? These take us back to even briefer instance, when our universe was hugely more compressed still. Ultra-early eras where experiments offer no direct guide to the relevant physics. And that's why at this point I should insert a health warning, because the discourse hereafter becomes more speculative. According to the popular inflationary universe theory, the entire volume we can now see within our telescopes has expanded from something literally that size. And moreover, it expanded up to that size with exponential growth from microscopic size, where the Hubble time during that growth was 10 to the minus 36 seconds. So this immensely speeded up version created the forebears of our present observable universe. The physics of that era is, of course, still speculative. It's far, far beyond the energy and densities that we can ever probe in the lab. But if we take inflation seriously and do the best we can, it has successes in predicting 2 features of the fluctuations in the microwave background, which I showed earlier, detected by Planck. First, that they are Gaussian, and secondly, that their amplitude depends on scales in a distinctive way, not quite white noise, but rather near to it, in a way that you can actually calculate. So inflation is not battle-tested because the key physics is still unknown, but there are good reasons to take it seriously because it does explain certain things that we observe in the universe better than any rival theory, certainly. But let's turn from the very beginning of the universe to the far future. Historically, if we go back to Eddington and Lemaitre even, they had 3 scenarios for the universe. Here again, time is plotted upwards. A universe which expands and then recollapses to a big crunch. A universe which expands and decelerates because of the gravitational pull of every galaxy and every other one, but not enough to bring the expansion to a halt. And a third option when the so-called Eddington-Lemaitre universe, when the universe starts to accelerate because it's got a non-zero value of what Einstein called the cosmological constant, lambda, and that eventually takes over and you get exponential acceleration. And I think it's fair to say that in the early 1990s, most people favored the middle version because we knew that the amount of material in the universe was about 30% of the so-called critical density, and so we expected a deceleration, but not enough to bring the expansion to a halt. But in 1998, astronomers had a big surprise. It was by then well known that the gravity of dark matter and ordinary stuff wasn't enough to cause a big crunch, and therefore we suspected that the universe would go and expand forever at a decelerating rate. But it turned out that rather than decelerating, if you looked at the Hubble expansion rate at high redshifts, it indicated that the expansion rate had accelerated. This was famously done looking at type 1a supernovae. So gravitational attraction in the recent universe was seemingly overwhelmed by a mysterious new force, latent in empty space, which pushes galaxies apart from each other. This could be Einstein's famous cosmological constant, as in the right-hand picture, or it could be something else, some other field. And according to Einstein's equation, we have to have positive energy but negative pressure. That's because rho plus 3p over c squared comes into the Friedmann equations, and you have to have negative pressure in order to get an acceleration. But incidentally, that's what you expect for a vacuum, because suppose you have a box of vacuum, it has positive energy in it, and you expand the box, you do PDV work, but after that you've got more vacuum. So the PDV work must be negative. So any energy latent in empty space has to have negative pressure and therefore give rise to an acceleration. I think many of us, if we just had the supernovae, wouldn't have believed it completely, but there was corroboration. And this takes me back to this Planck picture again. This big peak, the so-called Doppler peak, is a feature of the universe which represents the wavelength which has time to make just half an oscillation before recombination. And the angular scale on which this appears depends on the geometry of the universe. In a flat universe, it's about 1 degree. But if we were in a universe which had only 30% of the critical density and nothing else, then we'd be in a hyperbolic geometry, and it would appear at a smaller angle. So we have evidence just from this, which actually predicted the acceleration. And this evidence came first from Boomerang, a balloon experiment, was later corroborated by the others. And so we have this line of argument here. The angular scale of the Doppler peak implies a flat universe, and that implies that 70% of the mass energy is in a uniform component with pressure less than minus a third rho c squared, and that gives acceleration. So even if we didn't have the supernovae, we would predict acceleration there. But we've now got this nice, consistent set of arguments. And now a key issue is to determine the redshift dependence of the dark energy. If it's Einstein's lambda, it should be the same at all redshifts. But it could be something very much more complicated, which has a time dependence. And there are attempts, in particular, something called a dark energy survey going on at the moment, which are trying to map out what the Hubble constant is at different redshifts and how the clustering goes, to see if they can test whether the dark energy depends on cosmic epoch. The evidence is consistent with it being constant. But how do we know what the long-range future is if we don't know what the dark energy is? I think the best and most conservative bet is to assume it's something like lambda and stays more or less constant. And if that's the case, then the long-range forecast is we have more or less an eternity ahead, an ever colder and ever emptier cosmos, where galaxies accelerate away and disappear over an event horizon, rather like an inside-out version of the horizon around a black hole. And all that's left will be the remnants of our galaxy, Andromeda, and their smaller neighbors. Protons may decay eventually, dark matter particles annihilate, occasional flashes when black holes evaporate, and then complete silence. But here we must admit to some frustrations, and I entitled this talk Progress and Frustration in Cosmology. One frustration is that the vacuum energy is going to be very, very hard for anyone to understand. Because if we think of Einstein's lambda in modern guise, it means that there's some sort of energy latent in empty space. And most people suspect that empty space does have a sort of grainy structure, but on a scale which is a billion times smaller than an atom. This is a scale where gravity and quantum effects meet. And that's very, very far from any observations. And it's people like those who study string theory who are tempted to do this. The idea is that if you could magnify a bit of space to this huge extent, then you would find that what we think of as a point in our three-dimensional space is some tightly wrapped origami in 5 extra dimensions. And these are ideas, but they're very, very far from being anywhere near testable or being able to predict anything in our low-energy world which we can test, which would vindicate the theory. So we shouldn't hold our breath for a quick solution. And indeed, it may be that string theory could be correct, but the geometry could be too complicated for any unaided human brain to work through. Maybe it's got to await some sort of super AI which will tell us whether string theory is correct, whether it predicts the right masses for protons and things like that. If it does, we would then take seriously its cosmological predictions as well. So I think we shouldn't be surprised if the dark energy remains a mystery for a long time. But it's even more frustrating that we don't know what the dark matter is. The dark matter was first advocated more than 80 years ago by Fritz Zwicky here, and we don't yet know what it consists of. We have lots of ideas. We suspect it's some kind of particles, neutral particles made in the Big Bang, but there's no direct evidence from accelerators or from observations of what these particles might be. So they have the properties of a swarm of particles which don't interact, but we would like to know what they are, and it's frustrating that we don't. But going back, I'd like to make a sort of slightly curmudgeonly remark, because I'm sure you've seen this pie diagram, which shows the contributions to the present curvature or energy of the universe made by the different constituents. And you see that the dark energy is dominant. And I think this is misleading because it distorts the relative importance of the dark energy and the dark matter. Dark matter, 25% of the total, is crucial both within and outside galaxies, and was crucial in the past in controlling how galaxies formed. In contrast, the dark energy, which has a density that's uniform in space, and probably uniform in time too, is everywhere swamped by dark matter in the first half of cosmic history, and it's swamped by dark matter in all bound systems now. So it has no effect on clusters or on galaxies. So dark energy may be the number one challenge for fundamental physics, but it's almost irrelevant for astrophysics. So it is, as I said, far more frustrating that we don't know what the dark matter is, given that we've known about it for about 80 years. Let me now turn to another fundamental question. How much space is there altogether? How large is physical reality? Now, the reason this is a non-trivial question is, as I mentioned, there's a horizon set by our observations, even in principle, by how much the universe has expanded since the Big Bang. But there's no particular reason to think that that horizon is the limit of space, just as if you're on a ship, there's no particular reason to think the ocean ends just beyond your horizon. We don't know how far it goes on, but there's good reason to suspect that space goes on at least 100 times further than we can see. The reason for that is that if we look as far as we can in that direction and in that direction, there's no difference, even at the level of 1 part in 10 to the minus 5. So the gradient across that region of tens of billions of light years is very slight. So that suggests that if our universe is some large finite structure, it's much, much bigger than the range we can see, because we see only a tiny bit of the gradient. And it could be much, much, much more extensive still. It could stretch far enough that all combinatorial options are repeated. Far beyond the horizon, each of us could have avatars. And it may be comforting that if we make the wrong decision, there's someone out there far beyond the horizon that makes the right decision. But be that as it may, even conservative astronomers are confident that the volume of space-time within range of our telescopes, what astronomers have called the observable universe, is only a tiny fraction of the aftermath of our Big Bang. And this raises another query. The physical laws are the same everywhere we can observe. Spectra of the highest redshift objects show no change in the microphysics of atoms or their nuclei or the strength of gravity. But need that be true over this far vaster domain? And there's something else. Our Big Bang could be just one island of space-time in a vast archipelago. One Big Bang among many, as shown in this cartoon. Here's our Big Bang, the reason beyond our horizon, but that's just one of these sort of bubbles among many. And there's a very explicit version of this idea, what's called eternal inflation, which was developed about 30 years ago by Andrei Linde, a Russian cosmologist at Stanford. In his model, you get Big Bangs sprouting all the time from some substrate. It's a very powerful model, which works if the physics at that very early time has particular properties. As I said, we don't know whether it does have the properties which would create the multiverse in the nature that Linde talks about. Of course, mention of the multiverse often triggers the response that unobservable domains aren't part of science at all. But I want to contest this very strongly by a sort of aversion therapy, the process whereby if you're scared of spiders, you first have a little one a long way away, and then you end up with tarantulas crawling all over you. I mentioned that there were galaxies beyond our horizon. In a decelerating universe, they'd come within our horizon in the far future. So in principle, they'd be observable. But because they're accelerating away, then those galaxies now beyond the horizon will forever be unobservable. But does that make them any less real? I don't think it does. But since those galaxies would never be in principle observable, why is their epistemological status any higher than that of galaxies in the other quite separate space-times, which again can't be observed? It's of course not clear if there are other Big Bangs, but we'll only take them seriously if they're prediction of a unified theory which gains credibility by being battle-tested in other ways. But let me give an analogy for why we might, at some stage, take other Big Bangs seriously. We can't observe the interior of black holes, but we believe what Einstein's theory says about them because his theories gain credibility by agreeing with data in many contexts when we can observe it. Likewise, if we had a theory which described physics at 10 to the 16 GeV, that's the inflationary stage, then if it was corroborated in other ways, by, for instance, predicting correctly the mass of the proton or things of that kind, then it would be reasonable to take seriously its predictions where we can't directly observe it. And if it predicted physics which was required for Linde's multiverse, then we should take the prediction of other Big Bangs seriously. I should say we are not in that situation yet, but we might be one day. Indeed, a challenge for 21st century physics is to see which branch of this decision tree is correct. First, are there any other Big Bangs, or is it just one? Second, if there are many, are they all governed by the same physics or not? According to string theory, there could be a huge number of different vacuum states. So Big Bangs could cool down with a different vacuum and different microphysics. If that's the case, what we call the laws of nature may, in this grander perspective, be just local bylaws governing our cosmic patch, a cosmic patch at least as big as our observable universe. If physical reality is like this, then there's a real motivation to explore these counterfactual universes with different lambda, different g, and so forth, to explore what range of parameters would allow complexity to emerge. This is what's called anthropic selection, mentioned here. But some people foam at the mouth at the mention of the A word. However, quite apart from these motivations, some theorists might find it interesting just to ask what would happen if we tweaked the laws of nature in imagination. I think it helps to develop our intuition. It's like counterfactual history, where scholars speculate what might have happened if this nation had not lost the American colonies in 1776, and biologists speculate on how our biosphere might have been different if the dinosaurs hadn't been wiped out. So if you're allergic to anthropic reasonings, then just think it might be interesting to develop your intuition to think about these counterfactual universes. And I want to mention some of them. Universes which are slower, smoother, more chaotic, darker, and less polluted than ours. So first, what range of conditions is permissible for an anthropically allowed universe that could allow complexity? This is interesting because let's first take G. Supposing the gravitational constant were different, what would that change? This is a pedagogical diagram which Bernard Carr and I drew 40 years ago, and other people have drawn since, which shows on a log scale mass upwards and radius across. And you see on it that atomic nuclei and atoms on it, and you see black holes of slope 1. A black hole the size of a proton has a mass of 10 to 38 protons. Solid objects have slope 3, volume and mass going as the radius cubed, so slope 3 on a log-log plot. And gravity is unimportant for solids up to asteroid size, for sugar lumps, for rocks. But when you get up to the size of a planet, then gravity makes them round, and then we get up to Jupiter, then of course they start being squashed, and you get into the realm of the stars. This is very familiar stuff. And from diagrams like this, you could predict what stars were like, even if you lived on a perpetually cloud-bound planet. Here's a physicist's definition of a star, self-gravitating aggregate of that number of stars, which is the 3/2 power of the large number 10 to 38, which is the ratio of the gravitational to the electrical forces. Well, we can magnify some of the details of this, and I won't go into this, but if you're giving a course on stellar structure, you can show how stars of different masses have different properties, radiation pressure scales differently, etc. But the reason I show this is to say that if you change gravity, you wouldn't change the shape of this diagram at all. If you make gravity weaker, then of course stars, gravitationally bound fusion reactors would be smaller, and they would be less long-lived, and that wouldn't be propitious for complex evolution. But on the other hand, if you imagine gravity being a lot weaker, then you might have a rather better universe. Suppose gravity was 100 times weaker. Then the Chandrasekhar mass would be 1,000 times higher. The lifetime of stars typically 100 times longer. And indeed, if one makes that same assumption in cosmology, it turns out that if you leave everything else the same, the masses of galaxies scales the same way. They would be larger by a factor of 1,000 in that example. So the main point about this is that gravity must be weak, but gravity is emphatically not fine-tuned at all. In fact, the universe might be even more interesting if gravity was still weaker, which would be more space and time for emergent complexity, more powers of 10 between microstructures and those that are crushed by gravity. Now, what about another important cosmological parameter? I mentioned that galaxies have formed from primordial fluctuations. And I mentioned the fluctuations have amplitude about 10 to the minus 5. And this is a fundamental number, Q, which is the delta T over T across the sky for the fluctuations. And this is important because Q determines the scale of the nonlinear structure in the universe today and their gravitational binding energy. Q is 10 to the minus 5. The binding energy of clusters is 10 to the minus 5 c squared. Velocity of a 10 to the minus 2.5 c squared, that's 1,000 kilometers per second. And the nonlinear scale of the universe is Q to the 1/2 times the Hubble radius, that's 10 megaparsecs. So it is Q which determines the texture of the universe. So we can ask, since we don't know, even in inflation, what determines Q, what the universe would be like if Q was different. Suppose it was smaller. I call this an anemic universe, because then you get weakly bound systems forming later, and you might get stars but they may not retain their heavy elements, and so you may not get second-generation stars and therefore planets. And if Q were much less than 10 to the minus 6, then you wouldn't get any bound structures at all. On the other hand, supposing that Q was 10 to the minus 4, 10 times bigger than it actually is, then you'd find that systems, the mass of the coma cluster would condense at a redshift of 10, and they would cool down by constant cooling on the microwave background, and you get huge disk galaxies forming at a redshift of 10, as massive as a present-day cluster today. And there'd be a bigger range of nonlinear scales in our actual universe. But this might be a more interesting universe to live in than our present one, a bigger range of cosmic structures. But if you jack up Q still more, 10 to the minus 3, then you would find that nonlinear structures would condense out so early that they wouldn't fragment, they'd go into huge black holes, and you get a universe not very propitious. And of course, the other point is that if Q isn't much less than 1, then there's not a big range of scales between the fluctuations and the scale of the universe. So cosmology is only feasible because the fluctuations operate on scales small compared to the Hubble radius. It's like on an ocean where the biggest waves are still small compared to your horizon. But if Q were larger than 10 to the minus 3, it'd be more like a mountain landscape, where you can't really talk about average properties, and single entities may dominate the entire view. What about constraints on lambda? This is, again, fairly well known, that if lambda was too large, and if it dominated before galaxies had formed, then galaxies would never form. So lambda must be low in a universe like ours, although if Q, the fluctuation amplitude, was larger, then you could still have galaxies even if lambda was high. This is from a paper by Mario Livio and myself, where we plot lambda against Q, and if, for instance, the fluctuations were 10 to the minus 4, not 10 to the minus 5, then we could tolerate a lambda 1,000 times higher without it preventing galaxies forming, which they would form earlier. And of course, ideally, one would like to, if we had a theory, to test it by being able to put some measure on the probability of these different parts of parameter space. And just to mention a third thing that's important for our universe, and that's the nuclear forces. We know about stellar evolution, and we also know about nuclear synthesis, that a massive star has a structure where it has a sort of onion skin structure with the heavy elements being produced and then blown out. And this is a famous idea going back to the 1950s. And here's Hoyle and Fowler and Geoffrey and Margaret Burbidge. This was taken in 1971 for Willie Fowler's 60th birthday. But they, of course, developed this wonderful idea that we are all literally made from the ashes of long-dead stars, and they managed to explain quite a lot of the relative abundances in this way. Well, of course, everything they did depends on the property of atomic nuclei, the binding energy is a function of atomic mass. And there's been a lot of work done about whether fine-tuning is involved and what would happen if you change things. And of course, there's a lot of work on this by, in particular, Fred Adams at Michigan has done a lot of work on this. I don't have time to go into. But I would like to mention a rather extreme case, which is rather amusing to consider, and that is what I call a nuclear-free universe. This is a universe where you switch off the nuclear forces completely. And there's therefore nothing but hydrogen, nothing but protons. But let's suppose you leave everything else the same, gravity, the fluctuations, etc. Then you would get a universe which, on a large scale, looked more or less like ours. Galaxies would condense out, you'd still get cooling due to hydrogen, and stars would undergo Kelvin-Helmholtz contraction, but there'd be no nuclear forces, so they would go on contracting until they got down to the Chandrasekhar mass, which is 5.6 solar masses for a pure hydrogen star. And bigger stars would contract to black holes. So, in fact, the amount of energy you get out of stars is not all that much less than you get now. You get about 10 to the minus 3 of the rest mass, going to white dwarf, and if the black hole swallows up the star messily, you could get lots of energy out of that. Jupiter-like planets could exist, and as I said, the total radiation output is perhaps not much less than in the actual universe. But there's no chemistry, no rocky planets, no life, except perhaps Fred Hoyle's black cloud. That's the only kind of complexity which could exist if you just have hydrogen. So this universe, which would look rather like ours, would be in the same relation to our real universe that a marble statue is to a real human being. It would look the same outwardly, but it wouldn't have any sort of complexity. Just as a digression here, I'd mentioned that I wrote a book some years ago called Just Six Numbers, which discussed this sort of thing. And I've mentioned the various possibilities of what the universe might be like if you change the fluctuations, the density, or the nuclear physics. But what I didn't mention in this talk is, number one, if the universe had different numbers of dimensions. I mention that now because Gerald Whitrow was very interested in that. He wrote papers on what would happen if we had more than 3 dimensions. And he also had ideas about 2 different kinds of time in some of his ideas. So it's interesting that there are arguments that our universe is special in having 3 spatial dimensions and 1 of time. As regards fine-tuning, there is fine-tuning if you vary one parameter, but of course if you allow lots of parameters to vary, there's a whole range of parameter space where you could allow some kind of complexity to exist, but of course we don't really know what complexity is needed to provide genuine complexity that leads to intelligence and life. And just, I'd like to end by another historical flashback to planetary science 400 years ago, even before Newton. Because at that time, Kepler, there he is, thought that the Earth was unique and its orbit was related to the other planets by beautiful mathematical ratios, the Platonic regular solids, etc. Well, we now realize that the orbits of the planets aren't fundamental. They're historical accidents. They are determined by the history of our solar system. And the point is, it may be that just as there are zillions of stars, each with planetary systems, and Earth's orbit is special only insofar as it's in the range of radii and eccentricity compatible with life, so there are zillions of Big Bangs, and we are just in one of those which has the combination of parameters which allows complexity to emerge. So this is another way of presenting the flow diagram. Well, is it science? Some people don't like the multiverse idea because it would render the hope for neat explanations of the fundamental physical numbers as vain as Kepler's numerological search for ratios in the planetary orbits. A lovely idea, but it was wrong. And indeed, in this context, our preferences are irrelevant to the way physical reality actually is. So we should surely be open-minded about the possibility that we will experience a 4th and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there are zillions of planetary systems in our galaxy, then that there are zillions of galaxies in our observable universe. But we then realize that our observable universe is just a tiny part of a far larger and possibly diverse ensemble. So our perspective may be like that of a plankton in a spoonful of water that doesn't have any awareness of the rest of the ocean. Well, to address this question, we need huge advances in physics to know the probability distribution of different constants and the correlation between them. And that's a can of worms we can't yet open. We'll have to await huge theoretical advances. About 10 years ago, I was on a panel at Stanford University where we were asked how much we'd bet on the multiverse concept. I said, on the scale, would you bet your goldfish, your dog, or your life? I was nearly at the dog level. And André Linde, who had already by then spent more than 20 years promoting eternal inflation, he said he'd almost bet his life. And later on being told this, the great theorist Stephen Weinberg said he'd happily bet Martin Rees' dog and Andre Linde's life. Well, Andre Linde, my dog, and I will all be dead before any of this is settled, but it's not metaphysics, it's highly speculative, but it's exciting science, and it may be true. And I'd like to quote Hubble. He is smoking very heavily. He said in his book, Realm of the Nebulae, only when empirical resources are exhausted should we enter the dreamy realm of speculation. And to address the balance of this talk, let me finish by emphasizing that progress in cosmology in the last 50 years has been owed 95% to advancing instruments and technology, less than 5% to armchair theory. And I'd expect that balance to continue. But there's one big change, of course, brought about by the fact that computer simulations have hugely advanced in power and expanded in range. There's been huge progress in simulating the emergence of cosmic structure, incorporating gas dynamics as well as gravity, and these models have convincingly shown how the cosmic web develops. Feedback from stars and AGNs is still modeled rather crudely. 3D hydrodynamics, incorporating MHD, has allowed modeling of accretion flows. Jets in gamma ray bursts and active galaxies can also be modeled. Well, the 1960s were exhilarating for young astrophysicists. So much was new that the old guys didn't have a big head start over youngsters. But I'm not here to be nostalgic, because I think since there are students and postdocs here, I want to emphasize that today is an even better time for young researchers in astronomy to explore phenomena all the way from Mars to the multiverse. The pace of advance has crescendoed rather than slackened. Instrumentation and computer power have improved hugely, and still more will come online in the 2020s. We heard some of that in the earlier session today. And on that encouraging note, let me conclude, and thank you very much for listening. Thank you.
Martin, thank you very much indeed. So this talk is open for questions and comments. Quentin and then...
Thank you very much indeed, Sir Martin. It would be lovely to hear what Gerald would have said in response as well. On the idea of the multiverse, would there be a Big Bang to end all other Big Bangs? And if there isn't, would that tell us something about the multiverse?
Well, there would be. I think in most scenarios there is an infinite future. There's debate about whether there's infinite past or not. Some people say you can't go back in infinite past. Others say it could be like a grand version of the old steady state theory. So the infinite past is controversial, but I think an infinite future would be part of the scenario.
Yes.
Well, again, thank you, Professor, for such an interesting talk. The infinite inflation theory depends basically on the idea of spontaneous symmetry breaking, whereby the laws of physics fall out in one particular ensemble, in one particular case in our universe, and therefore if they then fell out in others. The question really is about the scientific method, in that, you know, science has always been based on observation and hypothesis being verified by observation, experiment, and possibly falsifiable experiments as well. Yes. If you say it's caused that the laws of physics fall out by spontaneous symmetry breaking, you are automatically bringing in the idea that there's an ensemble of other possibilities which require an ensemble of other universes. In other words, it's a circular argument. You're bringing in the assumption that there are other universes in order to confirm that there are such entities. Now, if it's a case of explicit symmetry breaking, there would have been some reason why these physical constants would fall out in the way that they did. But the very act of saying it's spontaneous removes the possibility or removes the question of what happened. In other words, it might be actually cutting off the scientific investigation about how these forces ended up having the values that they do.
Well, there's two things. I mean, of course, we know about spontaneous symmetry breaking in the electroweak transitions to account for why there's matter, not antimatter in our universe. And that's something which is not fully understood, but that is something which happened at some early stage in the universe. As regards the more exotic issue of the different vacuum states, I think we are very far from having any theory, but all I'm saying is that some of the people who work on string theory think there would be very, very many different vacuum states, and in each of them the microphysics would be different with different constants. Now, as I said, we have no idea whether that's correct at all. There's no reason to take it too seriously. But what I would say is that if we had such a theory and it had some empirical successes, if it did tell us why the three kinds of neutrinos, what their masses are and things like that, then we would take seriously its other predictions. And if it predicts the physics needed for Linday's eternal inflation, we would take that seriously. It's rather like, as I said, we take seriously what Einstein's theory says about the inside of black holes, even though we can never observe it, because we have good reason to take the theory seriously from other tests that have vindicated it. And so, likewise, if we have a theory that pertains to this very early stage, which is corroborated in ways we can test, then you would take seriously what it predicts even when we can't directly observe. So that's the best we can hope for. We may never get there, but that's what we would hope for, and that would put these ideas on a somewhat firmer footing.
I mean, my worry is that the scientific questioning would be short-circuited by simply saying, oh, the anthropic principle means that there is a multiverse.
Oh, no, I wasn't saying that at all. I mean, there could be just one universe with unique physical laws. I didn't say anything against that.
Yeah.
And even with the many Big Bangs, they could all have the same microphysics.
Last question, I think. Unless anybody has a theory of the universe that they wish to.
Right. Okay. Yeah.
In your cartoon showing the multiverse theory where each universe was expanding, it looked like they would join together. So in that theory, does that mean each universe sets off the next one? Or could the fluctuations occur such that they could spontaneously appear anywhere?
That was just a cartoon. I mean, there are some versions like that, but in other versions, there's a sort of exponentially expanding substratum, like a sort of mega steady-state theory, and Big Bangs condense out of it. And they then be completely disjointed and not connected. But there are lots of versions. There's another quite different version when we have a fourth spatial dimension. We have other universes which are three-dimensional spaces which are separated from ours because they're in some four-dimensional space. And just like you could imagine a whole lot of ants crawling around on this sheet of paper, a two-dimensional universe, being unaware of ants on a parallel sheet of paper. Likewise, there's a version of a multiverse where there's another space-time just that far away, but that distance is measured in some fourth spatial dimension, and we're imprisoned in R3. So there's lots of ideas. All I wanted to say, really, is that we have no reason to think that the domain we can observe with our telescopes now, or even in principle with our telescopes now, is more than a tiny part of physical reality.
Let's thank Martin Rees again for a super lecture. Thank you very much indeed.